Welcome to the Math Practice Standards webinar series. This webinar will provide you information on the second mathematical practice standard, reason abstractly and quantitatively. Let's start by reading this math practice standard in its entirety. This practice is short and sweet when you compare it to most of the others. After I read it, we will then unpack it piece by piece. Mathematically proficient students make sense of quantities and their relationship in problem situations. They bring two complementary abilities to bear on problems involving quantitative relationships: the ability to decontextualize, to abstract a given situation and represent it symbolically, and manipulate the representing symbols as if they have a life of their own without necessarily attending to their reference, and the ability to contextualize, to pause as needed during the manipulation process in order to probe into the reference for the symbols involved. Quantitative reasoning entails habits of creating a coherent representation of the problem at hand, considering the units involved, attending to the meaning of quantities, not just how to compute them, and knowing and flexibility using different properties of operations and objects. As you can see, Math Practice 2 covers several habits that students should be proficient in. Let's break down each section so we can fully understand each of these proficiencies. The first statement in this practice is all about understanding how many as it pertains to the problem. Which one has more or less? Are we getting larger or smaller numbers as we manipulate to solve? Also, at the most basic level, this could look like knowing 3 dogs are the same amount as 3 cats. Decontextualize means to take the information from the situation and write a problem using symbols. Example: in a story about 4 bears, students can draw out the number 4 and represent the bears by the number 4. If 3 more bears come into the problem, the mathematically proficient student can represent the amount of bears using the number 3. Then the child would add 4 plus 3 and realize the total is 7. The child has abstracted the bears, representing them by numbers symbolically, and manipulated the symbols as if they have a life of their own. They have turned concrete into symbols. Next is the ability to put a problem back into context, the symbolic back into words, during and after manipulation. So going back to the last example, the child would then be able to communicate understanding that the 7, the 4 plus 3, is actually a total of 7 bears. Math Practice 2 states that proficient students can create a representation of a problem, whether from the symbolic, 3 plus 4 equals 7, or from the unit values, 3 bears plus 4 more bears equals 7 bears. This is in reference to being flexible enough to use all operations in various situations. So now that you have a clear understanding of what Math Practice 2 entails, let's move on to the implementation of this practice into the classroom. This will involve the necessary planning needed for authentic tasks and problems to be incorporated in the lesson design. When I first started teaching, I had lesson plans that looked like a big calendar with page numbers on them. However, due to more teacher monitoring, we know that those days are gone. Today's plans, or shall I say today's lesson designs, are much more complex. It's important to choose activities deliberately. Choosing problems and activities that create the habits of mind won't accidentally happen. Think of the questions at the bottom of the page in a textbook. The students multiply 2-digit by 2-digit in 20 algorithm practice problems. Then there are 3 whole word problems at the bottom of the page. And guess what? All they have to do is pull out the 2 2-digit numbers and multiply. Surprise! This isn't reasoning. It's follow the pattern and repeat. With just a little bit of effort, we can do better. Planning for the math practices is looking at the actual student experiences that will occur as you teach the concepts. It's about how the students will be learning the concept. What will it look like in the classroom? In the early grades, having concrete representations is a must. No, you don't need real bears or lions, but small figurines, pictures, or manipulatives helps the students form a picture. Of course, word problems are a necessity. We need to ensure that students hear that the numbers represent something. We should also look for problems with flexibility and multiple solutions, like create a word problem that models 4 times 6. If it's your desire that your students are successful on those amazing, fun, standardized tests that we all love, then you know that being able to reason abstractly and quantitatively is completely built into the test. However, it's more than that. It's really built into life. But you can't expect a student to suddenly develop these habits on the day of the assessment. They have to practice them routinely. I tell my students that numbers void of meaning don't exist in real life. You'll never walk down the street and get hit by a 2. You may get hit by 2 rocks or 2 balls or 2 drops of rain, but never just a 2. Numbers are always tied to quantities of something. Just practicing 2 plus 3 in a textbook isn't enough to hone in these reasoning skills. They must be tied to meaning routinely. But how do we know that our students are developing the habits of mind that call for abstract and quantitative reasoning? We pose questions to the students, to ourselves, and eventually expect our students to pose these types of questions to themselves naturally. As you design your student experiences, you should constantly ask yourself if you are doing what it takes to create the essential habits of mind. Questions we should ask ourselves are, did I select engaging problems and tasks? Did I create the opportunity for the students to use mathematical reasoning and academic vocabulary as they worked and demonstrated understanding? Are my students being forced to contextualize and recontextualize? Here are some reminders as you design your student experiences. These questions will lead to better lessons. Do the activities and discussions in my classroom focus on students thinking how the algorithm represents the problem? Do I use rich tasks that involve students to create problems from numbers and vice versa? Do I focus on 1 or 2 problems for students to solve and discuss thoroughly, or provide a worksheet of problems to solve? Do I allow for students to visualize in these activities, abstract reasoning, understanding? As we get better at asking ourselves questions during planning, we need to train our students to ask questions themselves. Training should begin at a very young age and should create lifelong habits. As teachers, we should ask the students these questions as they are engaged in the tasks, but the emphasis is on the fact that we want to help them develop the habit of asking themselves these questions. What do I know about this problem? Can I explain the problem to myself or others? Do I understand what the numbers represent? Does that make sense? Does my answer make sense? How do I know? Are there any units involved? And do the units make sense? Many teachers create anchor charts. Also, many flip books with questions for each practice are popular resources. So now it's time to get more specific about the types of activities and tasks that it takes to provide the desired habits of mind for math practice 2. The key to reasoning abstractly and quantitatively is the ability to visualize. We first have to teach our students to visualize. By asking how many cubes are in this block, we're really asking the students to see all of the blocks, even the hidden ones. We're tuning the mind's eye. The problems and activities that we choose should emphasize this visualization. Let's complete this simple task. Imagine that this deck of cards only has 10 cards numbered 1 to 10 in order from top to bottom. Now visualize that you draw one from the top, then one from the bottom, then another one from the top, and another one from the bottom. And you keep doing this until you only have 1 card remaining. What number is on that card? How do you know? Personally, I had to use my hands and count out loud to get to the number 6, but I was also visualizing as I did the counting. This is the type of thinking or seeing that students proficient in Math Practice 2 can do. They can take words, turn them into pictures and numbers in their heads, and vice versa. So as we go through these next few tasks, pay close attention to the visualization that must take place in order for success to occur. Kendall and Macy went shopping. Kendall bought 3 shirts and 2 pairs of shorts. Macy bought 2 shirts and 4 pairs of shorts. Create the number sentence that represents the total amount of clothing that Kendall bought. Create the number sentence that represents the total number of clothing that Macy bought. Create the number sentence that represents what they bought altogether. This problem allows for students to transfer the words into symbols. It forces the student to focus on parts of the problem one at a time and comprehend what is happening. A first grader can also be asked to actually draw the picture that represents this problem. In addition, we could now write the problems 3 plus 2 equals 5, and 2 plus 4 equals 6, and 6 plus 5 equals 11. And the students can see how each of these statements could result in one scenario. In the higher grades, tasks for this math practice should focus on translating word problems into equations, number lines, using area models, tape diagrams, and units. Mathematical Practice 2 gives us language that shows students the relationship between the word problem, quantitative, and the algebraic equation, abstract. Most standard word problems are about quantities, asking how many animals, how much money, how many degrees. The possibilities are endless. When we take a word problem and translate it to an equation, we create an abstraction of the problem. For example, the equation x plus 6 equals 9 is an abstract problem. It could represent any of these situations. I received $6 from my cousin, and now I have $9. How much money did I have when I started? We went to the pet store and bought 6 more fish for our fish tank. We now have 9 fish in the tank. How many fish did we have before we went to the store? In 6 more years, I will be 9 years old. How old am I now? The quantities are dollars, fish, and age. The problems are quite different in that they are about different topics, but abstractly, the problems can all be represented by the equation x plus 6 equals 9. We take word problems or real-life situations and create equations that model the problems. This is one aspect of what it means to reason abstractly and quantitatively. The problem can be solved by subtracting 6 from both sides, given the solution x equals 3. Now we need to take this abstract idea and give it a quantity. For problem 1, it would be $3. The answer for problem 2 would be 3 fish. And problem 3's answer would be 3 years old. Our abstract solution, x equals 3, becomes a real-life quantity, dollars, fish, or years. But consider this question. How far did Ryan walk to school? 21 millimeters, 21 centimeters, 21 meters, or 21 kilometers? By focusing on the units, students must quantify one of each of these units and determine which is most logical. These students are developing strong number sense. They are becoming proficient in having an awareness of what numbers and units are and how they relate to one another. Being able to reason abstractly and quantitatively allows the student to understand a number's magnitude and what it means in problem situations. A number line is a very useful tool in the classroom. This type of problem easily lends itself to conceptualizing on a number line. Lee was reading a novel. He read 2/3 of a chapter each night. How many nights will it take him to read 13 chapters? But 13 chapters doesn't come out to a whole number. The rigor causes the student to reconceptualize once he gets to 13 chapters. 14 1/3 nights isn't an appropriate answer. The student must reason that the final chapter will be complete on day 15. Consider the academic discussion, the different entry points. What is the actual symbolic representation of this question? Could we write an equation? Is the number line the best way to solve this? Now we're getting into the facts that students reason differently and how exciting it is that different approaches can reach the same end target. Now I want to revisit a problem that we used to demonstrate Math Practice 1 makes sense of problems and persevere in solving them. It's easy to understand how a problem can be applicable to multiple math practices. This problem is a prime example of that. James went to the Boogie Ball. It was being held 15 miles from his home. He called the Orlando Diamond Cab Company for a ride to the venue. How much did his ride cost? Create an equation to represent his trip. Create an expression using M for miles to represent how much the Diamond Cab Company charges its passengers. The students definitely have to make sense of the problem and persevere because of its rigor. But this question is also asking them to turn the information that they find on the internet into a workable equation. Then they are made to go further and turn it into a generic equation that can be used for any amount of miles. Upon internet research, the students will discover that the first mile is $2.40, the constant, and each consecutive mile is $4.20. As they engage this problem, they will calculate the total price. But there is an additional rigor to this problem that isn't in the simple solve this equation. If the students persevere and answer the third part of the question, they discover that the generic expression includes $4.20 times n minus 1 because the first mile is represented by the constant. This engaging and rigorous problem takes perseverance and reason abstractly and quantitatively in order to be successful at solving it. And don't be surprised if this example or one like it is used in later discussions about other mathematical practices too. This question will take middle students 20 plus minutes to solve completely, but it is exactly the type of task that creates the habits of mind that is needed for proficiency. Now we will conclude this presentation with a quick discussion on how we assess Math Practice 2. Students can be assessed informally during this process just by asking questions as you circulate. But some teachers want a more formal rubric or checklist. I suggest allowing the written portion of each task to guide your evaluation of the student's problem-solving habits. Did they provide a thorough explanation of their solution? Did they create the symbolic representation accurately? Can they create an original problem using just the symbolic representation? This rubric can be used or adapted as quick reference to assist with that assessment. Students that are emerging from Math Practice 2 can reason with models or pictorial representations to solve problems. Students who are proficient in Math Practice 2 are able to translate situations into symbols for solving problems. And exemplary students can convert situations into symbols to appropriately solve problems as well as convert symbols into meaningful situations. It might be valuable to assess yourself also. This rubric is a great planning tool as you design your lessons, or just use it at the end of a unit. As we become more self-aware of the environment we create, and if it is effective in implementing the math practices, we should see a direct impact on the problem-solving and perseverance habits of our students. So as we conclude this webinar, consider the types of word problems you present to your students and the types of discussions you set up for them. We hope this webinar helped clarify your understanding of Mathematical Practice 2, Reason Abstractly and Quantitatively.